Good day. It's good to be with all of you again. Today we are going to talk about derivatives and integrals of vector-valued functions. Derivatives and integrals of vector functions. Derivatives. The derivative r prime of a vector-valued function r is defined in much the same way as it was for real-valued functions. dr dt equals r prime of t equals the limit as h approaches 0 of the quantity r of t plus h minus r of t all over h, provided this limit exists. The geometric significance of this definition is shown in the diagram to the right. So that's this one here. If the points P and Q have position vectors r of t and r of t plus h, let's see if we can understand that. So here's our P and here's our Q. Here's r of t. Here's r of t plus h. Then PQ represents the vector r of t plus h minus r of t, which can therefore be regarded as a secant vector. So r of t plus h minus r of t is this vector between point P and point Q. This is, again, that secant vector. So here is our space curve. You can see our points P and Q on the space curve. And r of t is pointing to P, r of t plus h, or r of t plus delta t is pointing to Q. And in this case, what we want to look at is the secant vector, which goes from P to Q. So this would be the PQ vector, which is r of t plus delta t, or r of t plus h, minus r of t. And you'll see that as t varies, of course, that secant is going to vary. We could also change the length, kind of like the t distance, the delta t between the 2 points, which would also change that secant. Longer secants, kind of a more of an approximation, shorter t secants, and we get a secant vector that's closer to the tangent vector, which is a foreshadow of what we're about to talk about next. If h is bigger than 0, then the scalar multiple r of t plus h minus r of t over h has the same direction as h approaches 0, it appears that this vector approaches a vector that lies on the tangent line. For this reason, the vector r prime of t is called the tangent vector. This would be the tangent vector to the curve, provided it exists and provided that r prime of t is not 0. This is shown on the right. So here's that same tangent vector, but you can see that as this point Q moves toward P, which is to say that h approaches 0, then our secant is going to approach some tangent vector r prime of t. Let's look at an animation. So once again, we have the same animation where we can see our secant vector between the 2 points. Here, what we want to point out is that as the delta t, which would be the same thing as the h, as delta t approaches 0, then our secant vector seems to be approaching a tangent vector. And if we divided by the h, or divided by the delta t, then that secant vector, a secant vector that's back here, will approach, notice, far away. Let's see if I can change my direction. Let's see, so here, you'll notice that you have that delta, the green vector represents delta r, or the r of t plus h minus r of t, And then we can divide it by the delta t or by the h, and that's going to give us this red vector. So there's the main one, divide it by h or delta t, and that's going to give us the red vector. As delta t gets closer to 0, you'll notice that the h vector is sort of staying kind of a similar lengthish. That's because you're dividing it by a smaller and smaller quantity. Okay. And you'll notice that the red vector now looks like it is tangent to the curve. We could see this more clearly. We could say, well, what happens when h approaches 0 or delta t approaches 0? And you would get just this r prime of t vector out the back end. So this is the tangent vector at p. We will also have occasion to consider the unit tangent vector, which is big T of little t, or big T of t, and it's equal to r prime of t divided by the magnitude of r prime of t. Notice this is the derivative vector divided by the magnitude of the derivative vector. So it's going to be a unit vector, and it's going to be tangent to the curve. This T of t is going to be a pretty big deal in the next section, where we will also introduce the normal and the binormal vectors. Let's show and manipulate where you can see the T of t relative to the r prime of t. So here we have a space curve. This particular one is given by t squared, comma 4t, comma 4 ln t, and it's for t bigger than 0. And so first of all, I want to point out that r of t is the description of the space curve. It gives you a position vector, and the tips of that vector are what trace out the curve. So remember, your position vector, yes, it starts at 0, but what's important are the tips of the vector, kind of the terminal points, not kind of where it starts. So that's r prime of t. That is r of t. R prime of t is a vector that lives on the curve and is always tangent to the curve. And so you'll notice it's that kind of like it's almost a tangent line, but it's not a tangent line, it's a tangent vector. And it might be a little bit difficult to tell, but that r prime of t can change in length. Let's see if we can see it. We rotate different angle. We see our r prime of t changing in length. It seems like it gets a little bit shorter in places. Okay. So that's r prime. So r goes from the origin out to the curve, but then r prime starts on the curve and it continues out, and its length is given by the derivatives of all the components. Well, when you find the length of that vector. Big T of t is a little different. It walks along that same direction as the red vector, except for its length is always the same. So notice the length is always 1. It's got this nice uniform length start to finish. And so it ends up being kind of our, like initial basis vector if we were to foreshadow linear algebra in terms of this space curve. So the unit tangent vectors change direction along the curve, but they always have length 1. And again, the unit tangent vector is easy to find. It's just the derivative vector divided by the magnitude of the derivative vector. The following theorem gives us a convenient method for computing the derivative of a vector function, r of t. Just differentiate each component of r of t. So if you have r equals to fgh, where f, g, and h are differentiable functions, then r prime of t equals f prime, g prime, and h prime. So notice all we're doing is differentiating each of the 3 functions. Pretty easy. Example 1, find the velocity, speed, and acceleration of a particle whose motion in space is given by the position vector r of t equals to 2 cosine ti plus 2 sine tj plus 5 cosine squared t k. So first, let's look for our velocity. Using what we remember from calculus 1, we remember that the velocity, or we can expect that the velocity vector is simply going to be equal to r prime of t, which would be, in this case, -2 sine t, 2 cosine t, and it looks like 10 minus 10 cosine t sine t. That's our velocity function. To find the speed, we need the magnitude of the velocity function. So speed, or maybe we'll call this s of t, will equal the magnitude of the velocity function, which would be the magnitude of r prime. And this would be the square root of 4 sine squared t plus 4 cosine squared t plus 100 cosine squared t sine squared t, all under the radical, which I think simplifies. Notice that you have a sine squared plus cosine squared, which is 1. So 1 times 4 is 4. So I think this simplifies to the square root of 4 plus 100 cosine squared t sine squared t. And notice that the speed function, s of t, is not a vector valued function. It just gives you a number for any given t value. Also remember that this will not be the same thing as 2 plus 10 cosine t sine t. In order to simplify the radical, you would need to factor this thing into a perfect square, and that plus is a big warning sign for us. Lastly, we want to find the acceleration. So acceleration. And again, recalling what we've done in the past, we could guess this will be a of t, definitely a vector, and it's going to be v prime of t or r double prime of t. And this would be, in our case, equal to the derivative of negative sine t, or -2 cosine t, comma, -2 sine t. And now we're going to have to use the product rule, but we actually really don't like the product rule because it's complicated. So maybe we'll use a little trig identity and remember that 2 cosine t sine t would be the same as sine of 2t. This is the same thing up above as -5 sine of 2t. And the derivative of that will be -10 cosine of 2t. So there is our velocity, speed, and acceleration vectors. In example 2, we are asked to find the unit tangent vector of the curve r of t equal to 3 cosine t I plus 3 sine tj plus t squared k. So to do this, let's begin by recalling our formula. So remember, the unit tangent vector is equal to r prime of t divided by the magnitude of r prime of t. And this is a formula that you will want to have memorized. So it looks like we need r prime of t. And that will be derivative of cosine is negative sine. So I have minus 3 sine t, comma 3 cosine t, comma 2t. And the magnitude of this quantity is square root of 9 sine squared t plus 9 cosine squared t plus 4t squared. Notice we have a sine squared plus cosine squared, which is 1. I've got 9 plus 4t squared. Square root of 9 plus 4t squared. 9 plus 4t squared is not a perfect square, so it can't be simplified. Again, this thing is not equal to 3 plus 2t squared. But we're able to combine our r prime of t and our magnitude r prime of t and draw our conclusion. So thus, t of t, the unit tangent vector, is equal to 1 divided by the square root of 9 plus 4t squared times the vector negative 3 sine t, 3 cosine t, and 2t. And that is our unit tangent vector for the given curve. We next have a theorem which gives us properties of the derivative process with vector valued functions. And the important thing to note here is that all of these properties behave as you would expect them to. So, theorem. Suppose u and v are differentiable vector functions, c is a scalar, and f is a real valued function. Then, 1, d dt of u of t plus v of t equals u prime of t plus v prime of t. Addition works as you would expect. 2, d dt of c times u of t is equal to c times u prime of t. That is, scalar multiplication and derivatives work the way you'd expect. 3, d dt of the quantity f of t times u of t equals f prime of t u of t plus f of t u prime of t. That is, the product rule works the way you'd expect it would when you have a function and a vector valued function multiplied by each other. So notice f as a function, our old-fashioned real valued functions, and u is a vector valued function. So product rule works the way you'd expect it to in this case. 4, d dt of u of t dot v of t is u prime of t dot v of t plus u of t dot v prime of t. Notice here, u is a vector valued function, v is a vector valued function, and what you get out the back end is exactly what you'd expect from the product rule. So once again, the product rule works the way you'd expect it to with the dot product. 5, d dt of u of t cross v of t equals u prime of t cross v of t plus u of t cross v prime of t. Notice again, u of t is a vector valued function, v of t is a vector valued function, and what you get out is exactly what you would expect if you use the product rule. So the cross product works the way you'd expect it to, namely using the product rule. 6, d dt of u of f of t equals f prime of t times u prime of f of t. Here, notice again that f of t is that real valued function, but you're going to get the derivative of the inside times the derivative of the outside function evaluated at the inside function. The chain rule works exactly like you would expect it to. So notice that for all of these rules, they all work as you might expect. So while it's important to have memorized the product rule, the dot product, the cross product, the chain rule, you don't need to memorize anything from this particular theorem, because everything in this theorem works exactly like you would expect it to, provided you know your dot product, cross product, chain rule, and product rule. Integrals. The integral from a to b of the vector valued function r of t dt equals the integral from a to b of f of t dt I plus the integral from a to b of g of t dt j plus the integral of from a to b of h of t dt k. Here, of course, we are again assuming that r of t equals f of t comma g of t comma h of t. So this means that we can evaluate an integral of a vector function by integrating each component function. We can also extend the fundamental theorem of calculus to continuous functions, continuous vector functions, just typo here, continuous vector functions, as follows. The integral from a to b of r of t dt equals the antiderivative of r of t, so big R of t evaluated from a to b, that is big R of b minus big R of a. Example 3. Suppose r of t equals cosine ti plus j minus 2tk. Evaluate the following integrals. In A, find the integral of r of t dt. So this will be equal to the vector, which is made up of the integral of cosine t dt, comma, the integral of 1 dt, comma, the integral of negative 2t dt. So this will be sine of t plus c, comma, t plus c. And here we notice that our c's might be different. So maybe we'll call the first one c1 and the second one c2, comma, negative t squared plus c3, because this is an indefinite integral. And then notice that c1, c2, c3 are constants. So we might write this as the integral of the vector sine t, comma, negative t squared plus some c vector. So I've combined my c1, c2, and c3 into some c vector. In part B, we want to evaluate the definite integral from 0 to pi of r of t dt, where r is as given above. Now, conveniently for us, we've already found our antiderivative. So we know this will be equal to a vector sine t, comma, negative t squared, evaluated plus c, evaluated from 0 to pi. Well, at pi, this will be sine of pi is 0. This will be 0 pi negative pi squared plus c minus sine of 0 is 0. T at 0 is 0. Negative t squared at 0 is 0. Also plus c vector. We'll notice that you have a plus c vector minus a c vector. And so those are going to cancel just like they have in the past. And we're left with just the vector 0 pi negative pi squared. That's how you evaluate a definite integral of a vector valued function. Example 4. Suppose that we don't know the path of a hang glider, but only its acceleration vector, a of t, equal to negative 3 cosine t I minus 3 sine t j plus 2k. We also know that at takeoff, or time equals 0, the glider departed from the point 350 with velocity v of 0 equals 4j. find the glider's position as a function of t. So we might expect, and rightly so, that if we have a, we're given the a vector, then the velocity vector will be the integral of the a vector, and the position vector will be the integral of the velocity vector. The challenge here is going to be, of course, doing the integrations, but mostly in finding our constants of integration. So first, let's find v. So to do that, we know that v of t is going to be equal to the integral of the acceleration vector, which is minus 3 cosine t minus 3 sine t and 2 dt. So the antiderivative of negative 3 cosine t would be negative 3 sine t. The antiderivative of negative 3 sine t would be positive 3 cosine t. And the antiderivative of 2 would be 2t. And then we have to, of course, add in our first constant. This is a vector. And I say first constant because I know I'm going to have to integrate a second time to find the position function. Okay, so we found v. And the second part of this is find v, including its constant. So to find its constant, we take advantage of the fact that we're told that the initial velocity was 4j. And so we can say, we know that v of 0, which according to the formula above will be negative 3 times the sine of 0, or 0, comma 3 cosine of 0, which would be 3, and 2t evaluated at 0, which would be 0, plus c equals 4j, which would be 0, 4, 0. So I think it should be clear from this. We have the 3 in the middle term of v of 0 with the plus c. We have the 4 there. So I think it should be clear that our c vector is going to be 0, 1, 0. So now we want to find r. That would be the position function. And we remember that r of t is equal to the integral of the velocity function, which we've just found. It's going to be the integral of negative 3 sine t, 3 cosine t plus 1, and 2t dt. The antiderivative of this will be, well, antiderivative of negative sine will be positive cosine. So I have 3 cosine t, 3 sine t plus t. The antiderivative of 1 is t, and t squared, plus a constant. Maybe we won't call it c again. Maybe this time I'll call it d, since we already used our c up. So we found our position function, but it still has this constant hanging around. And so we've got to find that constant of integration d. Please recall that we were given that the launch value was 350. So we're finding r, including its constant. And so we want to find r of 0. So r of 0 will be 3 times the cosine of 0, which will be 3. 3 sine of 0 plus 0, which would be 0. And t squared of 0, which would be 0, plus d. And we're given that this is going to equal 350. So the 3's match, but clearly we need d to account for the 5 in this middle term. So we can conclude that our hang glider follows the path r of t equals the r of t that we found earlier, 3 cosine t, 3 sine of t plus t, and t squared. But we also have to add in plus 5 to account for the constant of integration for that initial position. So we have found our position function. So there you have it, derivatives and integrals with vector-valued functions. You'll notice that this doesn't really seem that hard. So there's some basic integration, some basic differentiation, but really the only challenge is that you're integrating or differentiating multiple times instead of just once. In terms of pictures, we have a nice picture to go with the derivatives, but there isn't a really nice picture to go with the integration. And that's okay, and also a foreshadow of the fact that we don't often integrate with these vector value functions unless we're doing it in these kind of application senses, like in the hang glider example that we just completed. Hope that helps, and I look forward to catching you on the next video.